Hello! Today I want to talk about two topics, reference and bias. And when we say reference, we usually mean something that is constant or independent of both voltage and temperature. Bias is usually referring to bias current. So to put our transistors in the correct operating mode, we need a bias current. So I'm going to introduce the topics today and pose a few questions that I want you to think about. So let's start with our trusty old symbols, or actually what the goal is. So we want to understand why do we need these references and a few things on the circuit architectures. Let me move my mouse. So when we set up a simulation in SPICE, then we use these two independent sources, a voltage source and a current source. Now, in SPICE and the differential equations that is solved internally in SPICE, it is quite simple. The voltage source is zero impedance. It will force a voltage into a node no matter what you do in the circuit. If you put the voltage source to 1 volt, it will be 1 volt between the plus and the minus. And the current source is similar. It says, okay, I'm going to push a current into the node pointed to by the arrow of a certain magnitude, let's say 1 microamp. And it's going to push that current no matter what the voltage on that node referred to ground is. Now, these two sources are very useful in SPICE simulation, but they don't exist in the real world. There is no such thing as an independent voltage source, or indeed an independent current source. It always has some non-idealities. The voltage source will have a source impedance, which changes the behavior across, well, voltage and current. And the current source will have a parallel impedance that can change the voltage over frequency and at DC. So what do we do then on chip? Well, we have to think about this concept of voltage, because all through the studies we often talk about the voltage in a node. We say, okay, this node is at 1 volt, this supply is at 1.8 volt. But when we go back to the equations and look at sort of what do we mean by voltage, it is always referred between 2 points. There is no such thing as the voltage in a node. The only reason we have that is because we've sort of come to an agreement that we refer all voltages to this magic place called ground. And in a real circuit, in a real integrated circuit, this ground will usually be off chip. Now, even on the PCB, the ground will not be perfect. There's going to be resistances going all the way from different points on the circuit to this point. There's an impedance there, and it can depend on time, on voltage, on frequency and temperature, and on process. So if we, on one part of the chip, create a constant voltage, and we actually want to distribute that across the chip, that is actually very hard, and sometimes you just have to do that. Sometimes you cannot do the alternate route, which I'll explain in a moment. But sometimes the accuracy requirements for this voltage is such that you can't do anything but actually make sure that it becomes the same voltage on the other side. Because imagine in this scenario, we build up a voltage VR that we know that is constant, that doesn't change with temperature. But this impedance to ground, that can change. And the impedance on the other side might be different. And there might be current, or at least over frequency, there will be current flowing in the wire from the source to the destination. So it's actually very, very hard to make sure that the voltage that we want to use on the other side, for example, in an analog to digital converter or similar, is actually the same as the VR. As such, quite often what we do is we convert this constant voltage into a current. Now, there's readily available resistors on chip, and they have a quite large variation, maybe plus minus 20%, but they are very well matched. And usually if I now insert a resistor on the destination side of the same type that I use in my voltage to current converter, then I can match the voltage within a few percent. But if I have to go more accurate than a few percent, then you actually quite often have to go to a voltage distribution. But this is good to know. And quite often that means that a central sort of component on the chip will be this reference voltage and the current. And then you can distribute the current multiple places on the chip. It is also a bit simpler to copy current than it is to copy a voltage. When you copy a voltage, well, you can hook up all the destinations to the same voltage, but imagine what happens if one of the circuits is badly designed or maybe haven't thought about everything, and it actually kicks back noise onto the voltage line. That will then distribute to all the different destinations. Now you can of course insert buffers like a unity gain amplifier, but that adds offset, so it goes into your error budget for this reference voltage. But what I want you to think about is what quantity do we actually have available on an integrated circuit that is independent of process, voltage, and temperature. Now I'm going to talk about one today, but think a bit more about this. Can you think of something? But quite often you end up talking about something called a band gap voltage reference. So this is a circuit that somehow is related to the band gap of silicon. And when we talk about band gaps of silicon, we're talking about semiconductors and sort of p-n junctions, or indeed bipolars. In this case, I have a diode-connected bipolar. And we can look at the current and the voltage across the base emitter junction, so from the base to the emitter, in this type of circuit. Now, we know it's going to be, well, it's going to have a current. In this case, actually, we have set the current. And that current's going to be equal to, I don't remember, is it saturation current we call it? Oh yes, it's basically a very small current, usually on the order of 1 picoampere. And then we have this known exponential relationship where we have the base emitter voltage divided by the thermal voltage, so KT divided by Q. And then there's going to be some leakage in any junction, and we just signify that with -1. And in this case, for a diode-connected bipolar, you'll also have a base current going into the base. Now, if you just use a diode, then this base current drops away, but the equation here stays the same. Now, since this IS is very, very small, and this is probably microamps, we can usually ignore this -1. And let's, for the sake of argument, also ignore the base current. Although at 1 microamp, you might actually have to think about it. In any case, we can simplify the equation, and then we can rearrange it a bit, so we can see that the base emitter voltage is equal to K times the temperature in Kelvin divided by Q times the logarithm, or the natural logarithm, of the current divided by this IS factor. Now, my question to you is, how does this VBE change with temperature? Think about it. Try to figure it out. And if you can't figure it out, I'll explain it, well, when we meet. Or you can look in the lecture notes. I'll also explain a little bit there. But that's not going to come out for a while. Now, when we talk about band gap circuits, there are many different types. What I show here is a way to generate a current that is proportional to temperature. And in this case, it is actually the voltage across this resistor that becomes proportional to temperature. Now, looking at the previous equations, we can see that, let's just ignore that it's a VBE, but call it a diode voltage. It's basically the same thing. We can see that this would be the equation for both the diodes. Now, there is a scale relationship, so this is 1 to n, so this is n times larger, and that actually means the IS of that device will be, I think it's going to be larger. So, when you work into this, you will discover that the voltage across this first diode is going to be higher than the voltage across this larger diode. And that means there will be a differential voltage across this resistor. So it's since we use this op amp to copy the first diode voltage to the second point here. And this differential, that's really cool, because that differential voltage is actually proportional to temperature. And that sets the current in this circuit. But to work out exactly why and exactly the equations, you can try that on your own, but we'll get back to that in the lectures. Now, of course, there's an op amp in here, which means that op amp will introduce some error sources. For example, the open loop gain of the op amp matters. The output resistance of these PMOSs matters. The offset of this op amp matters. But that's part of the design stages of getting to a good current source that is proportional to temperature. So, I'm going to give you a hint about diode voltage. So when we look at this equation, the knee-jerk reaction is to say, oh, the VBE is proportional to temperature. You can see that, right? VBE is equal to something that's, well, we multiply by temperature. But that initial knee-jerk reaction is wrong. It is not correct. When you work out the equations, and you have to dig quite deep to find the equations, you can actually see that this VBE decreases with temperature. So it's what we call complementary to absolute temperature. But how can we combine those? A complementary current to temperature and a positive temperature, positive coefficient. How can we combine those two to get a constant voltage? Because it is possible. This is a band gap I simulated last year, and we can see that the variation across from -40 to +125 is not many millivolts. It's about 2 millivolts, and that actually comes from the equations of the diode. Now, of course, when you simulate corners and look into corners, it's going to change because properties of the diode voltage or VBE voltage might change. It might be the doping, it might be lots of things. The diffusion constant for electrons, it might be the lifetime of electrons, it might be the intrinsic carrier concentration, potentially. And I would encourage you to actually look into the equations, dive a bit deeper on the diode voltage, because you start to then realize that multiple factors matter. And I can ask another question. Hopefully I remember in the lectures to ask you what you think, but I believe also the direction of the bipolar, or how you lay out your diode or bipolar device on the chip, will matter for this constantness over temperature. Now, once we have the voltage, then we need something to convert to a current. Now I'm just going to state that this is a voltage to current converter, but I want you to try and figure out how it works. Have a look, try to think it out, and we'll discuss it in the lecture. Now, the standard band gaps that you'll find in the book and other band gaps, they usually produce a voltage that is a bit higher than the band gap of silicon. So band gap of silicon is around 1.12 volts, but most band gap voltage references will give an output voltage on the order of 1.2 volts. It depends a bit on technology, but it is possible to make a low voltage band gaps, which you sometimes have to do in nanoscale CMOS, for example, if you don't have access to a higher voltage. But quite often, in most integrated circuits today, at least sort of fully integrated circuits, you will have a higher voltage. It's common to have a 3 volt or a 1.8 volt or something that is high enough to make a standard band gap. And I would encourage you to try that first before you try this low voltage band gap. But to get to how the low voltage band gap works, we sort of use the same circuit. Now we know that the voltage at the top of R1 here, that is the same as the diode voltage. And then in this picture, I've used a unity gain buffer to put that across a resistor. So what we know is that this current that flows through this branch and through this resistor, that actually has to increase with temperature, because I've said the voltage across this R1 is proportional to temperature. But the voltage across the resistor, that's different, because that's the diode voltage from the first diode voltage here, copied to this side and then copied all the way over here. And that decreases with temperature. So the voltage across this resistor decreases with temperature. So then we have a current that decreases with temperature. Now, if we could sum these two currents somehow, then maybe we could make a current that is stable across temperature. So I want you to try and convince yourself that in this circuit, that is exactly what happens if you scale the resistors right. Oh, one note, is the current through R2 the same without the OTA? I should point out, I mean this OTA, not this one. That's the same. But the unity gain buffer, the OTA used as unity gain buffer, that's gone. Okay. We'll go through more details in the lectures, and I want you to ask questions. For bias, it's quite often that we just need a current. And actually in the lecture, I'll ask me and I'll give you some example of some really quick and dirty ways to generate a current when you don't want to faff around with sort of larger bias current sources. What you see here on the picture now is actually one of the most common topologies for a bias current generator. The idea here is to set up a current such that we can actually copy we can just hook on more PMOSes up here, and we can create multiple copies of the current. But I wanted to try and work out why it is so that whatever impedance you put here, you're going to get, as long as you scale this 1 to 4, and as long as your NMOS transistors are in strong inversion, and as long as the strong inversion model or the square law model is true enough, then you're going to get the case that the transconductance of the transistor is actually proportional to 1 over Z. And that's quite cool, because this is quite often referred to as a GM cell, because you can get a transconductance that doesn't vary that much over process corners, because it's set by this resistor. And extreme cases, you could actually trim this resistor also. But I've said Z here, sort of impedance, for a reason, because what you put here does not need to be a resistor. It can be something else. So try to think about what that could be. So that's the introduction video for the next lecture. I'll see you then.